As an example about transformers, we are doing problem 6.8 out of the text. The transformer that we're talking about is not actually an ideal transformer. If you're looking, it's in figure P6.8, and what it is we have a wire that lies along the x-axis. I'm going to draw our coordinate system first. And here's our wire. That is carrying a current I. Did I say x-axis? I meant z-axis. And then we also have, let me change colors here. We also have a toroidal ferrite core with some turns of wire wound around it. So it looks like this. So this actually is a transformer's problem, but it's not necessarily an ideal transformer because not all of the flux due to the wire is going to be captured in this coil. But here's what we have to figure out how to do. First of all is they ask us to develop an expression for VEMF. First of all, let's find the magnetic flux density due to this wire. So we're going to say B1 is the magnetic flux density due to the wire. We know it's phi directed. This is a mini Ampere's law problem. And we know that if we were to define some sort of Ampere's law contour, let's say that way, we could say that the current flowing through that contour is equal to the closed loop integral of the magnetic flux density around the contour, around the boundary of the contour, of the surface. So this current flowing through the center of the contour, that's easy. That just works out to I because we have a simple wire carrying just the current I. And the magnetic field, if you use the grab the wire technique, is flowing around the wire right-hand rule-wise as usual. So it's going to be phi directed because of the symmetry of the problem. There's no angular dependence, there's no z dependence of the whole situation. Which means that this contour integral on this side works out to 2 pi r magnitude of B, whatever B is. B1, let's say. So our magnetic field, our magnetic flux density, excuse me, equals phi hat I, oh, and there's supposed to be a mu here, divided by 2 pi r. Now if we want the flux through this loop, because that's how we're going to find VEMF, right? Using Faraday's law, VEMF is minus the time derivative of the flux B dot ds going through the loop. How do we do that? Clearly the loop that we're going to define to do this flux integral is right here. So we are going to be integrating, and this toroid has some boundaries that I think are going to be useful to you, and those are that it has height c, and it has inner radius a and outer radius b. So the horizontal dimension of this loop is b minus a, or of the little surface that we're doing the integral through, the flux area. All right, let's do that. To write that out, we have minus the time derivative of the integral from 0 to c along z, and from a to b along r, of mu I over 2 pi r phi hat. And let's choose our surface direction. Let's see, our direction needs to go from the positive terminal to the negative terminal, right? Yes, so the contour needs to go from the positive terminal into the negative terminal, so it needs to go that way. Which means that our surface normal vector should be coming out of the loop towards us in the phi direction. Okay, so that means that ds is phi hat. Let's choose this location to be along the x-axis, so we only have to do, well, we're doing dr anyway, so dr dz. All right. Evaluating it, nothing here depends on z, so we can evaluate this part of it right away. What we end up with is minus the time derivative, because we haven't done anything with that yet, because we haven't put in any expression for this current, which is going to be where our time variation comes in. And all of this stuff except for the r can come out to the front. So mu I c over 2 pi. The remaining part of the integral is the integral from a to b of 1 over r dr, because as you know, phi hat dot phi hat just works out to 1. The integral of 1 over r gives you ln of r, and we're going to evaluate that from a to b, which is ln of b minus ln of a, or ln of b over a. So VEMF then becomes minus d dt of mu I c over 2 pi ln of b over a. Now, if we want to calculate the value of that EMF, we need to choose some value for the current.